Today we calculate the cell potential if the standard cell potential given for the reaction is 3.17 volt. We know that to calculate the cell potential, which we also call as EMF, is using the Nernst equation. Now in the given Nernst equation, we need to find N as well as the concentration of product and the concentration of reactant. Now first we go for finding the value of N. So first we write down the oxidation half followed by the reduction half of the given reaction. So we know that Mg becomes Mg2 plus with the loss of 2 electrons. Similarly, Ag plus becomes Ag with the gain of 1 electron. But we know that in a cell reaction, the number of electrons for the oxidation half and the reduction half should be same. So how do we make it same? By multiplying the reduction half with 2. So therefore it becomes 2Ag plus 2E minus, which gives 2Ag. Now let us look at the concentration of product and the concentration of a reactant. Product is Mg2 plus, concentration of Mg2 plus into concentration of Ag. But for Ag we write here to the power of 2 because here the coefficient 2 is there given for Ag in the reaction. Similarly, for the concentration of reactant we write Mg into concentration of Ag plus, and for Ag plus also we write raised to the power of 2 because here the coefficient in the reaction is 2 for Ag plus. The concentration for Mg2 plus given is 0.130 and the concentration of Ag plus given is 0.0001. So we write the 2, and for the respective metals in their elemental form we take for granted the concentration as unity or 1. So we get log to the base 10 of concentration of product upon concentration of reactant. Now let's solve this particular portion. So here first thing is to remove the decimals. So 0.0130 we write it as 130 upon 1000, and in the same way 0.0001 is we can write it as 10 raised to minus 4. And how do we get it? First we write it as 1 upon 10 raised to 4, and when we remove the reciprocal we write it as 10 raised to minus 4. Similarly, with the further calculations we get here as 13 upon 10 raised to minus 6, which we can also write as 13 into 10 raised to 6. So when we solve this we get 13 into 10 raised to 6, and we find the log further. We solve it. We write it as log of 13 into means we write here plus log of 10 raised to 6. Log of 10 raised to 6, we know that the answer is going to be 6. Whatever is the power that will be written here, the same will be written here as log of that number. Same way, for log of 13 we need to find log of 13. We need to use the log table where we need to write the characteristic and find the mantissa. Characteristic we know how to find. Since there are only two numbers here, so we write 2 minus 1. So the characteristic is 1 here, and log of 13 we need to see. So we come to know that log of 13 is 1139 because we see it under 0, as after 13 there are no more numbers. So log of 13 we get as 1.1139, which we are going to write here in the bracket because 0.03, once we remove the log we need to put it here within the bracket, and then we go in for adding these two and we get 7.1139. And then after multiplying, now here comes many of the students, they leave the sum over here or find it difficult to do the multiplication using decimals. So the easy way is to remove the decimals and multiply them. After you get the answer, you need to see that after the decimal how many numbers are there. So what do? We know that here there are 2 and here there are 4 numbers after the decimal. So that means in our answer also, after the decimal, 2 plus 4, 6 numbers should be there. So after multiplying and when we get the answer, after that we know that after our decimal there should be 6 numbers. So there are 6 numbers. So we understand that we need to place the decimal here. So we get the answer as 0.21. Don't take the entire numbers. Only take the initial 2 or 3 numbers. So we are taking here 0.21. Subtract them and we get the final answer as 2.96 volt. So the cell potential E cell is 2.96 volt for the given reaction.